Well, okay, so where is it? This is, you have a concept. So, you go to the station. Yeah. And you go over. Yeah. I don't really get it. Yeah, it's literally like just two walls. Yeah, it's just all this green around it, like loads of lights. It's very like tracking.
Anybody need this?
Feel like I don't know. Thanks. Well, I will share guys.
Yeah.
Just a lot. Just only two lines.
Okay. I'm running out. Any answers? So we did this. We did this once before. Now, for some reason, what I brought is last year's homework, which was a different graph, but the same question. Okay, if you're here to talk, then just sign in and go away, please. Thank you. Okay. I've got to bring the solution that I have from the previous one. But, so the idea was that for each of the arcs, you have a decision variable. So there would be x, SA, SB, SC, and so on. So x UV for each arc UV. Okay. And then you wanted to leave S. So when you add all the okay, so what are they? I didn't say what they are, but I'll say it. So they're all binary, so they're all 0 or 1 variable. And for each of them, you're saying whether the particular arc that the variable is therefore is used in the shortest path or not. So it's 1 if it's used, and it's 0 if it's not used. So you want to use exactly 1 because you want to leave that vertex over there. That's a constraint. So these are variables. Constraints. You want to arrive in T exactly once. So x AT plus x BT and CT should be 1. And for all the other vertices, for A, B, and C, you want to come there. If you come there, you want to leave, and if you don't, you want to not leave. Okay, so this is expressed. For example, for A, you will have all the arcs that are coming into A, so that's just XSA. The sum of all those variables, which is just this one variable, has to be equal to XAB plus XAT. Okay, so what this tells you is what this is telling you is if this is 1, that means that you're going from S to A on your shortest path. And then you have to decide whether you're leaving from A to B or whether you're leaving from A to T, but you can't just disappear. Okay, so if this is 1, that sum has to be 1, so exactly one of those variables also has to be 1. And if you decide not to go from S to A, so if this is 0, then you can't continue from A. Okay, that's the meaning of this. constraints. Okay. So they're all 0, 1s, and they're telling you whether you're using that R or not. And then you have the same thing for B. So what is going into B is AB, SB, and CB. And what is leaving B is just BT, I think. Okay. And you have the same idea for C. So SC is CB plus CT. Is it all right? Well, yeah. If you find something that I've missed in what do we get? Oh, and then for each UV, you want that variable to be 0, 1 variable. Okay. And the objective for the purposes of this exercise doesn't really matter too much, because the question is whether the constraint matrix is totally unimodular, and that doesn't depend on the objective at all. But we can say that the objective was to minimize, and I think I should call it W. So WUV X UV over all the arcs or edges, whatever you call them. Okay, that's not so important. And the W's are the numbers, are the lengths. So WUV is the length of that particular arc. But like I said, the objective is at the moment is not very interesting to us. What we want is to have a look at the constraint matrix. So, what does the constraint matrix look like? It has, okay, ignoring this bit for a while. Okay, so this binary, I don't care so much about, because they're not going to spoil the total unimodularity. What happens is practically you have one constraint for each of the vertices. So this one is for S, this one is for T, and this one is for A, B, and C. Okay. So each of the constraints is somehow indexed by a vertex S, T, A, B, C. And then the columns correspond to decision variables, and we said we had one decision variable exactly for each arc. Right. So if I list them here, SA, SB, C, what else do I have? AB, CB, ATB, TCT, is that everything? There's a hole in the paper, so there will be a hole in the matrix. This will need to go here. Okay. Okay, now this is somewhat there will be trouble now. Because how do you write well, so okay, so what I'm trying to do, just to, hopefully everybody knows what I'm trying to do, but in case people don't, what I'm trying to do is I'm trying to write the constraint as a x. What am I trying to do? Is equal or less than or equal to b? So I'm slightly in trouble there. But that's okay. So an easier goal is probably to write ax equals to b, because I have equalities in all these constraints. Right? So that's so first try that, and we should kind of what I want is to have all the two variables on one side of the equation and all the constants on the other side of the equation, and I don't have that here. And I want the matrix to be totally unimodular, so I need to do some on it as well. Okay, so what I want is to have 1 here and -1 here, and I'll tell you how I got it. And I want 1 here and -1 there, and I want 1 here and -1 there. Now for AB, I want 1 there, -1 there, and for CB, I want 1 there. For AT, and for BT, I want 1 there, -1 there, and for CT, I want 1 there and -1 in T. So I'm just going to make it clearer what is where. Might even make it less readable. Okay, so that wasn't great. But the remaining values are all zeros. Okay, so you can imagine that. Okay, so the first constraint, like this in the matrix, that is quite nice because it says XA plus XSA plus SP plus SC equals something. I'm not giving you the right-hand side because that I don't care about either. Okay, so the right-hand side would be 1, B. I've got another one. I've got -1s, and I have +1s there. But that's an easy fix because this constraint is the same as if you write -XAT minus XBT minus XCT equals -1. Okay. So I rewrite it like this. And the purpose of rewriting it like that is that I want every column to sum to 0. That's my. And so now I have it. So, okay. So this constraint is -1 and 1 and 1, and that is because I can write this constraint as -XSA plus XAB plus XAT equals 0. Okay? And it's the same for the remaining two constraints. So now I've got a matrix. The question is this matrix totally unimodular? And the answer is yes. It's a bit of a trick. So we looked at this condition at the bottom. Okay. So each entry is +1, -1, or 0. That is definitely true. Each column has at most 2 non-zero entries. Well, that is also true. So exactly 3, exactly 1, 1, exactly 1, -1. And the rows can be partitioned into 2 parts so that in each column with 2 non-zeros, the sums of the 2 parts are equal. Now that's a bit tricky. How do you split it? So last week, if you recall, we had a by part type graph. So these vertices were on the left and on the right, and we split it on the left and on the right. But here, can't do it because the vertices are not on the left and on the right. But the answer is we can split it by putting everything on the left and nothing on the right. Okay? And if everything is on the left, the sum is always 0 because there's exactly 1, 1, and exactly 1 minus 1. And the sum on the right is also 0 because there's nothing there. So you're adding in, and then you get 0. So this condition is also satisfied. So, so that tells you that the matrix is totally modular. And then you use, well, yeah, and that's basically the answer. There are some details around, because you should also reconcile the difference between these two formulations. We're looking at the equality and dealing with inequality, and that's not a big deal. And another thing which is not a big deal is that we have to add this. But this is basically adding the identity matrix down here. And we already did that last week. And we said that it doesn't destroy total modularity, so we can do it. Any questions? So why is it important that it's totally unimodular? What is it good for? Reminder. Anyone? Anyone remember? No? Nisha's looking it up at least. Yeah? Do you want to tell us? No? Okay, fair. Yeah, well, there was this. Because of this. So this theorem is saying that is that when you solve the LP relaxation of that integer problem, so the first thing you do whenever you're doing your branching problem, for example, you will always get an integer optimal solution, so there's no branching, so it's essentially simpler to solve than the integer programming in general. So if you're doing shortest paths, or what we did last week, the maximum matching problem using integer programming, simple to solve. The first LP relaxation will solve it. All right? That's why it's interesting and nice. Any questions? No? Okay, so for today, we should do something. Has everybody got the handout? One page. No? Where are the spare ones? Can you pass it to the back somewhere? So what we want to do is look at one of the following two problems. College timetable and exam scheduling. and write a simple integer programming model for one of them, because there's not enough time for both. But have a quick look, and I'll do the both. Which one you want? Ready? I didn't do a Kahoot, so we'll do it the old-fashioned way. Who would like exam scheduling? It's just me. Who wants a college timetable? Oh, everyone. Okay, so take 5 minutes to read it, so we all know what we're solving. What?
All of the names make sense. But the top one doesn't make sense.
Which means cheese. It's cheese.
Yeah, like what's this gonna do? Good one. I've been thinking that I've done that. I didn't say it out loud.
Okay, it's a serious matter. It's not my fault. I didn't create it. It's from a book. It's not my work. Okay, everybody ready? Okay, good. Now, so what are the three things we need for a formulation?
Decision.
Yes, and constraints. Yes. Exactly. So, come on, concentrate, focus. Okay. I'll give you the decision variables. Well, no, I won't give you the decision variables. Starting again. Start again. I'll give you the decision variables in a bit. I forgot that we should so we should put some notation. So we've got teachers. Okay. So I'll So I'll introduce a set of teachers. So what do you want the set of teachers to be called? I'll call them T. It's not wobbly. Wobbly T would be something like. This is a curly T. Okay. Set of teachers. What else do I want? It's a curly T, not a wobbly T.
Not a J either.
A curly J would be something like this. Okay. And then, what else do I want? C, so that's the set of classes. There are two classes, 1 and 2, right? These. And then we have time slots. So what do I call them? S. That will be it.
As if that's curly enough.
Hmm?
As if that's curly enough.
This is a curly S. So this is the set of time slots. So what are the time slots? There are, what does it say? It's like Monday, Tuesday, Wednesday, Friday. 8, 10:15. And 16:15. Okay, right. So I'll call them 1, 2, 3, 4, 5, 6, 7, 8, and so on. And this one is 20. I think it is. And that's just to make life simpler or more difficult, depending on whether you like numbers or whether you like complicated. Okay, now I think the last thing we need is the number of classes. So we know the number of classes. So for each teacher and class. We know the number of classes that they have together. So this will be the number of lessons by teacher T in curly T for class C. So these are the things, these are the numbers in the table that you have. Okay. So pretty much all the data we have. We have some more constraints there that sports on those days. That will come in constraint. Now, decision variables. Has anybody got a guess what they're going to be? What about them? Well, you know how many you're supposed to have. But what is the problem? What do you want to know? Well, you want to know which lesson comes into which time slot. That's the whole purpose of making a timetable, which is a very hard problem, as you can probably tell from the results of all timetables. I don't think I'm supposed to mention this during the student service. Anyway, so yeah, so our goal is to find out which lesson given by which teacher or which class is going to fall into which of the time slot. Kind of the objective. And when you're doing an integer programming formulation and things like this, then the standard way of doing that is I'm sure you know, is to create binary variables for each of the possible things. Okay, so for each lesson, class, and time slot, you create a 0, 1 on whether that lesson is taking place in that time slot. So that's also what we're doing here. Give me a letter for the decision variables. L. Curly or L looks like 1 or a capital L. Alpha. Big L. You can't write small L. It looks like this. It looks like capital L. Okay. So we need a 1 for each teacher, class, and slot. Okay, so this is going to be 1 if teacher T takes on class, no, how do you write it? Takes class C, 1 or 2, in time slot C. And 0 otherwise. So when you want to solve something, anything in integer programming, typically this kind of scheduling, well, all kinds of problems you will have.
Should that time slot S in S rather than 2 and 2?
Usually have 0, 1 variables. Stop interrupting me. No, well done. Yes, yes, you're right. It should be time slot S. No, you're quite right. Sorry. I appreciate it. So one of the first years in the lab said a couple of weeks ago, asked me whether his LP formulation was correct, and I said yes, it's correct. Serious? I know you like a cookie. He didn't even believe me that I just say that the formulation is correct. And it's actually correct. Anyway, let's do the constraints. So give me a constraint for a function.
The sports lesson can only take place on Thursday afternoon in 4 and 6.
Sports lessons take place. Yes, that's right. So that's kind of a special one. So that we know. Okay, so L for Mr. Muscle, class 1, and slot. Which slot is it? Thursday afternoon. Thursday 15. And slot 15 has to be 1. Okay? That must be there. It can't be anywhere else. Well, no, it must be there. If it can't be anywhere else, I haven't said yet. But, we'll follow it anyway. And what is the other one? Biceps. Class 2, slot 15 also has to be 1. Okay, that's good. Good start. So that's the sport is Thursday, 4 p.m. Okay. Any more constraints? I don't know.
Well, it's
16.
because the thing tells you it's between 2 and 4.
Is it between 2 and 4?
Yeah.
Oh, sorry, it has to be between 2 and 4, not 4 and 6. You're right. It should be. This is 16, but yeah, I got confused. This one's 15, so yeah. So correct one's 15. Yeah. So next constraint. It is. Okay, so one of the constraints is that we have to have the correct number of lessons for each training. So for every teacher and for every class. Curly C. So for every teacher in class, we need that the number of lessons they're giving to that class is exactly that number that we know from the table. So what is the total number of lessons they're giving? Any guesses? All of them guess. You look like you've got a guess. Yes. What is 13? I don't know what 13 is. What I want is a formula that gives you, based on the decision variable, that gives you the number of lessons. And where you get it is you look at all the slots and add all the decision variables with this particular T and this particular C. Okay. So for every teacher, for every class, you add all the decision variables that belong over all the slots, so all the 20 L's that belong to them too. And you have to get exactly as many ones as you need. Okay? Is that clear? Good. Then there's something that you don't want to happen, and that is conflict. You don't want one teacher to be in two places at once. Okay. And you don't want one class to be in two places at once. So what you need is so for every teacher, I'm rushing it a bit. I shouldn't be, but almost running out of time. And for every time slot, so in every time slot, you want that every teacher is teaching no more than one lesson at the same time. Okay. So again, you have to add all the LTCSs. This time over all the classes. This is giving you, for every teacher and for every time slot, how many things that teacher is doing at that particular time of the week. And you don't want them to do more than one thing. So this can't be more than one. With sums and things like that, probably takes some getting used to, but and you don't want the same, so it's kind of the same thing you want for the classes. So for every class and every time slot, when you add all the teachers they have in that particular time slot, should be no more than one. Okay, and there's this thing that tells you that one teacher can have that class only once a day. Okay, that's so how does one do that? So for every teacher and for every class, oh, and for every day as well. Okay, so days will be 1 to 5. You want the sum of that teacher doing that class in that slot to be no more than 1. And that's the 3 formulas. So this is my way of so on the first day, you want S to go from 1 to 4. On the second day, you want S to go from 5 to 8. On the third day, you want it from 9 to 12, and so on. So I think these formulas work as giving you the time slot in particular. Okay? Agree. Check it. Agree. Okay, so this is no more than once per day. And there are some silly constraints which Monday morning. Okay, so for every teacher and for every class, Monday morning has to be free. So LTC1 is 0. Monday morning, just no lessons are allowed, I think. And insulin doesn't work Wednesday. So for every C and for every time slot, but this time only from, what is the Wednesday, 9 to 12? And then there's another one. Oh, yeah, sorry. So for FX, same thing. But for S, so Monday mornings, is that 1, 2? And this doesn't fit, but it should be binary. Oof, I think we've done it. Were there any missing bits that we haven't covered? Besides the objective. I think it's hard enough as it is. It doesn't have to have an objective. But the book I got it from suggests that the objective should be to minimize the holes in the timetable. Which is probably a reasonable thing to do. But yeah. Okay, so this is a formulation. If you get incredibly bored during the week, you can try and solve it using local. Otherwise, I'll see you on Thursday.